this video we'll look at magnetic induction and talk about something called magnetic flux and what is meant by the induced EMF. So the science understanding for today, straight out of the SACE outcomes, is listed here. So this is what we are going to cover. It's also what you're expected to be able to explain and the problems you're expected to solve for this content. Firstly, I'm going to start you off with a video by Crash Course. This is a good little YouTube video that kind of summarizes what we're about to talk about in this video here.
Physicists learned a lot about electricity and magnetism in the 19th century. We've already talked about one of the biggest discoveries, that electric currents can create magnetic fields. And once scientists had figured that out, they wondered if the opposite was also true. Could magnetic fields create or induce an electric current? Many physicists designed experiments to detect electric currents induced by magnetic fields, but they kept coming up empty. That is until two physicists, Joseph Henry and Michael Faraday, both on their own figured out what was happening. It turns out that magnetic fields do induce electric currents, but only under certain circumstances, when the magnetic field is changing with time. And this discovery is eventually what led to the invention of hard drives. When Faraday discovered that magnetic fields induce electric currents, he got kind of lucky. He set up a current flowing through a coil of wire so that it would generate a magnetic field. And then he watched to see if that magnetic field induced a current in a second coil of wire. And it didn't, which was probably pretty disappointing at first. But then Faraday noticed something weird. When he turned the current on and off in the first coil, there was a brief spike of current in the second coil, but only while the current was changing from off to on and back again. He realized that he had been looking for the wrong thing. A constant magnetic field didn't cause an electric current in a loop of wire. Only a changing magnetic field did. These days we call this idea Faraday's law of induction. It says that a changing magnetic field will induce an EMF in a loop of wire. An EMF, you'll recall, stands for electromotive force, which is what causes electrons to move and form a current. So now Faraday knew that when a magnetic field changed over time, it induced an EMF in a loop of wire. But a couple of other things induced EMF too, even if the strength of the magnetic field stayed the same. Changing the area of the loop of wire induced a current too, and so did changing the angle between the loop and the magnetic field. That's because of a property that most directly induces EMF, the property known as magnetic flux, represented by phi b. Magnetic flux is essentially a measure of the magnetic field running through a loop of wire, and when that field changes, that's what induces an EMF. And there are three factors that affect the magnetic field, and therefore the magnetic flux through the loop. First, there's the strength of the magnetic field, which we label as B. Next, there's the area of the loop, A. If the loop is bigger, there'll be a larger magnetic field running through it, and vice versa. And finally, there's the angle theta between the magnetic field and the line perpendicular to the face of the loop. Combining all these factors, we find that the magnetic flux is equal to the strength of the magnetic field times the area of the loop times the cosine of the angle between the magnetic field and that perpendicular line. And if the magnetic field and the loop are perpendicular, then the magnetic flux will just be equal to the strength of the magnetic field times the area of the loop. Magnetic flux is measured in units of Tesla meter squared, also known as Webers. But when it comes to inducing EMF, what really matters is how the flux is changing over time. If the magnetic flux through a loop of wire decreases over time, the EMF increases accordingly. And if the flux increases over time, the EMF decreases. In maths terms, we'd say that the EMF is equal to the negative of the change in flux over the change in time. This equation works well for the change in flux through one loop of wire, but often you'll be inducing an EMF in a coil of wire, like what Faraday was doing in his experiment. So it helps to know how a change in the magnetic flux will induce EMF in a coil. And the key here is that a change in the magnetic flux through the coil induces the same EMF in each loop of the coil. So if you want to know the total EMF in the coil, you calculate the EMF for one loop of wire, then multiply it by the number of loops in the coil, or N, which means that the induced EMF in a coil of wire is equal to the number of coils times the change in magnetic flux over the change in time, all multiplied by a negative sign. So having two loops in the coil would mean double the EMF that would be induced in one loop, while 10 loops would mean 10 times the EMF. So Faraday's law of induction lets us calculate how much EMF, and therefore how much current, will be induced in a loop of wire by a change in magnetic flux. But in what direction will the induced current flow? To figure that out, we use a rule called Lenz's law. You know how currents generate magnetic fields? Well, Lenz's law says that the magnetic field generated by the induced current will be in the direction opposite to the change in magnetic flux. So if you know the direction of change in magnetic flux, you can figure out the direction of the magnetic field generated by the current. And from there, you can use our old friend, the right-hand rule, to figure out the direction of the current. To get a better feel for how to apply Lenz's law, let's look at two scenarios involving a bar magnet below a loop of wire, with the north pole of the magnet facing the loop. In the first scenario, you'll move the north pole of the bar magnet closer to the loop, which increases the magnetic field flowing through the loop. This therefore creates a change in magnetic flux and induces a current in the loop. And the current generates a magnetic field that opposes this change in magnetic flux. Now the north pole of the magnet points in the same direction as the magnetic field. So by moving the magnet closer to the loop, you essentially made the magnetic field from the bar magnet point more strongly upward. And according to Lenz's law, the magnetic field created by the induced current will oppose this, so it will point downward. In the second scenario, the north pole of the magnet is again facing the wire, but this time you move the magnet away from the loop. In this case, you're basically making the magnetic field from the magnet point less strongly upward and more strongly downward. So the magnetic field created by the induced current will point upward to counteract this change. And once you know the direction of the magnetic field generated by the induced current, you can figure out the direction of the current from there. This is where the right-hand rule comes in. Make a stop sign with your right hand, then point your thumb in the direction of the magnetic field being generated by the induced current. The direction that your fingers are pointing, that's the direction of the current. Let's try it. In our first scenario, where we move the north pole of the magnet closer to the loop of wire, the generated magnetic field was pointing upward, so the current will be moving clockwise along the loop. In the second scenario, where we move the north pole of the magnet away from the loop, the generated magnetic field is pointing downward, so the current will be moving counterclockwise along the loop. Now, another way to use magnetic flux to induce a current in a loop is by changing how much of the loop is within the magnetic field. Say you have a horizontal magnetic field and a loop of wire. You arrange the loop so it's perpendicular to the magnetic field, then drag it out of the magnetic field, which decreases the amount of magnetic field within the loop. The magnetic flux through the loop changes, which induces an EMF. The strength of the EMF is equal to the negative of the change in the magnetic flux over the change in time. The flux, you'll recall, is equal to the magnetic field times the area times the cosine of the angle between the magnetic field and a line perpendicular to the loop. Since the magnetic field is perpendicular to the loop, the cosine of the angle is 1, so that term drops out of the equation, which means that in this case, the change in flux is equal to the magnetic field times the change in the area of the loop within the magnetic field. And the area of the loop is equal to its length, which we'll call L, times the width of the loop that's in the magnetic field, which we'll call X. As you move the loop out of the magnetic field, the amount of its width within the field, X, changes. So, the change in magnetic flux is equal to the strength of the magnetic field times the length of the loop times the change in its width within the magnetic field. So the strength of the induced EMF will be equal to all of that divided by the change in time. Thankfully, there's a way to simplify all of this. The change in x over the change in time should look familiar. It's just equal to the velocity of the loop as you move it out of the magnetic field. So when you move a loop of wire in or out of a magnetic field, the strength of the induced EMF is equal to the strength of the magnetic field times the length of the loop times the velocity of the loop. Using a magnetic field to induce a current is useful for all kinds of reasons. We'll talk about some of the main ones next time. It's also how hard drives work, at least the ones that use a rotating disk. Your computer stores information on your hard drive by magnetizing small sections of the disk. To read that information, your computer rotates sections of the disk past the head, which is a small electromagnet that has a coil of wire. The changing magnetic field induces a current in the coil in the head, and computers process that signal as the zeros and ones we use to store digital information.
Okay, so magnetic flux is a measure of the number of magnetic field lines passing through an area. So it's kind of like a quantity of stuff passing through a certain space. The magnetic flux through an area, which we use the symbol capital A, is defined as the product of the magnetic field strength and the area. So from that we get this Greek symbol phi, which is magnetic field strength times the area. So for a larger magnetic field strength, because they're directly proportional, we can see that the flux will increase, or if we increase the amount of area that we're catching, then flux will also increase. So you can kind of think of it as a net and the magnetic field lines being the fish. The more fish we trap in our net, the larger the flux, the quantity of fish we're catching increases. From the image that you've seen and can see on the right, you can kind of tell intuitively that the angle is going to have some effect to it. So if I want to catch the most number of fish as these magnetic field lines, then I want it to be perpendicular, because for the same area, if it's perpendicular, it's actually going to catch more lines than, for example, if it was 90 degrees to it, or parallel. So we often define the flux as the product of the magnetic field strength and the area perpendicular to the magnetic field. So rather than just saying at some area, we define it as the area perpendicular. We could therefore explain this or express this as a component, where we just say it would be BA cos theta, where at a maximum a value of 1, that's when it's 90 degrees, it's perpendicular, and at a minimum value of parallel, we virtually catch nothing and this becomes 0. So theta is the angle between the area and the line normal to the magnetic field, which is the important aspect there. This creates the general formula for any area at any angle to the field. So the flux is BA cos theta. This is what we saw in the video earlier. So the magnetic flux is the strength of the magnetic field, the area of loop, times the cosine of the angle between the magnetic field and a line perpendicular to the face of the loop. The units of flux from the formula above would be basically a combination of what units we've got. So magnetic field strength times by area gives us that magnetic field strength is Tesla and area is meters squared. So we end up with this Tesla meters squared. And we often refer to a Tesla meter squared as the Weber. We use the notation capital W lowercase b, and this is the SI unit. So magnetic flux's unit is the Weber, which is represented as Tesla meters squared. Given that this equation uses the area, and you're going to involve formulas using areas of shapes and things like that, a quick recap on converting squared units, because this is a common thing that people make a mistake in. So fairly basic, but 10 centimeters squared we know is 10 centimeters times 10 centimeters. So if I'm going to convert each of those into meters, I end up with a 0.01 meter times 0.01 meter. And then when we actually multiply these numbers, the decimals increase. So we end up with 0.0001 or 1 times 10 to the minus 4 meters squared. So it's not a case of just changing the square meters by a decimal place. It actually increases or decreases by a certain factor. So in general, centimeters squared to meters squared, we times by 10 to the minus 4. If we had millimeters squared and we want to go to meters squared, we times by 10 to the minus 6. So just be careful when you're converting, if they give you an area in centimeters or millimeters, that you use this method rather than just converting the value, say 10 to 0.1. Practice question for you. So calculate the magnetic flux through an area of 2.3 times 10 to the minus 2 meters squared, placed at a right angle to the magnetic field, given the magnitude. And this question here, 16 centimeters squared, the angle is 60 degrees and the magnetic field is 3 Tesla. So the question was cut off, but basically calculate what the magnetic flux of this object is. Be careful about the units, so make sure that you note this is centimeter squared, not meter squared, which we need, so you're going to need to convert in this question. So have a go at these.
It's astounding. Time is fleeting. Madness takes its toll. But listen closely.
Not for very much longer.
I've got to keep control. I remember doing the time war, drinking those moments when the blackness would hit me and the void would be calling. Let's do the time war again. Let's do the time war again.
It's just a jump to the left.
So on the first question, we simply plug in the numbers and we get 3.7 times 10 to the minus 2 Webers. Remember, Webers is the SI unit. And the next example, you could draw a picture if you wanted to help figure out what's going on. We convert the units, we times by cos 60, and we get 2.4 times 10 to the minus 3 Webers. Okay, electromagnetic induction is the next piece we're going to look at. So a potential difference is induced, which means it's generated in a conductor that is moving relative to a magnetic field. The potential difference causes the current to flow if the conductor is part of a complete circuit, and this effect is known as electromagnetic induction. So it's all about inducing a potential difference. Rather than generating one by just putting charges, we actually create one from a magnetic field. Some important conclusions are drawn from this example that we have. A potential difference is induced when the magnet is moved in and out of the coil of wire. No potential difference is induced when the magnet and the coil of wire are not moving relative to each other, and the current flows in different directions depending on the direction of motion of the magnet relative to the coil of wire. So it all depends on the motion. These experiments were first performed by English chemist and physicist Michael Faraday in 1831. He realized that the potential difference was induced whenever the magnetic flux through the coil of wire changes. The magnetic flux increases when the magnet moves towards the coil due to an increase in magnetic flux density, because we're getting closer and closer to those magnetic field lines where they're closely bunched closer to the object. And he also noted that the magnetic flux decreases when the magnet moves away from the coil, given that we're decreasing the magnetic flux density. Remember that flux is kind of the how many magnetic fish lines we're catching in our net. The movement of the bar magnet toward and away from the coil results in a change of magnetic flux through the coil. This change in flux induced a potential difference in the coil of wire. Therefore, the induced potential difference in the conductor is referred to as an electromotive force, so EMF. This EMF, electromotive force, causes the current to flow if the wire is part of a complete electrical circuit. So in this picture here, you can see a straight conductor of length L. It's moving at a speed v at right angles to a uniform magnetic field that's acting into the page. Because we can see the feathers coming out of the page, we know that the arrow of the magnetic field is going in. So if we consider this situation, electrons in the conductor are forced to move with the same speed as the conductor, and therefore they experience a force. This force is given by the formula QVB sine theta, which just equals QVB, as the theta part is 90 degrees, it's perpendicular to the field. So if we use the right-hand rule, the electrons are going to flow from the left end of the conductor. This means that one end of the conductor has an excess electrons and the other end lacks them. If they're being forced to one side, they're bunching up more on one side of the conductor than the other, they're not evenly distributed, and this generates a positively charged end. This shows that the left end of the conductor becomes negative relative to the right end because that's where the electrons are bunching up. This then creates an induced potential difference, or an EMF, between the two ends of the conductor, given that they now have a charge. We've created a potential difference. The EMF will increase until it balances the magnetic force acting on the electrons and stops them from moving. So from here, have a look at page 219 and question 1 to 4. This uses some of the stuff that we've talked about now, so magnetic flux questions and a very basic introduction to this electromotive force.